How to do sentiment analysis on movie reviews. This tutorial is based on the book Deep Learning with Python. The author is François Chollet. By the way, he is the creator of the Keras. Thanks him to make the examples of the book available in Jupyter Notebook. Just click in the link below to access the Python code for free from his GitHub. Let's load the Internet Movie database. We import Keras, and from Keras dataset we import the Internet Movie database. We save the data in train labels, test data, and test labels. See that you put number of words 10,000. That means we restrict our analysis for just the 10,000 most common words in the movie reviews. If you run the code in Anaconda or Google Colab or any version of new NumPy, you're likely to get this error message. To solve the problem, you can go to the search Stack Overflow and see several different solutions. I will give you the code that I think is the best solution. Let's import NumPy and load the old version with the old parameter where pico equal true. Now we can load the dataset without any problem. And let's reestablish the actual NumPy. I prefer this solution because I don't need to downgrade to the old version of NumPy. We have 25,000 movie reviews in the training dataset, and more 25,000 reviews in the testing dataset. 50% of the reviews are positive. That means they love the movie or they at least like. The other 50% of the reviews is negative. That means they dislike the movie or hate the movie. Let's see the first observation in the training dataset that has index 0. The words from movie review were converted to numbers. Now let's see the label of the first observation. It is 1. That means positive. Suppose you want to decode back these numbers to English or words. Here is the code. Keras has inbuilt functions to deal with a string or text. For example, this get word index. The data is in a dictionary form. You just have to revert back. Let's decode back the first observation of index 0. Remember, Python starts count from 0, not 1. And here is the first review. This film was just brilliant, casting, location, scenario, and etc. If you want to read the other reviews, just go and change the index. You have more than 25,000 reviews in the training dataset. Remember that you have just one explanatory variable in this dataset that is represented by numbers. For neural network, we have to vectorize this one explanatory variable. That means we are going to transform this one explanatory variable in 10,000 dummies. Remember that we restrict the analysis for the most 10,000 common words in the reviews. The first step is to create this matrix with 10,000 columns with all zeros. Then, if the words show up in the review, you fill with the number 1. Now, let's apply the vectorization to the training and the test dataset. See now that the first observation has 10,000 explanatory variables, and the values of these explanatory variables are 0 or 1. The labels y, they are already 0 and 1. Let's just put them as array format. Next step is start to building the neural network. From Keras, let's import models and layers. This is a typical classification problem that can be handled by a sequential model. Sequential model is known as Feedforward neural network. That means the information flow from the inputs X to outputs Y without any feedback. Let's build the first layer. We start with 10,000 inputs, that are 10,000 dummies for each word. Then we apply the rectified linear transformation and output 16 neurons. Let's formalize the intuition mathematically. We have 10,000 explanatory variables X, and W's are the weight or the slopes of X. The logic of the gradient is get these 10,000 optimum W's that minimize the loss function and get the best prediction. Then we added B1. This 1 stands for the first layer. We call this term bias in machine learning, but it's just the intercept. This is just a linear combination, ordinarily square. The rectified linear unit takes the maximum between 0 and this ordinarily square term. In other words, negative values are eliminated. The intuition is that the rectified linear function takes linear inputs and it makes a nonlinear transformation, but keeps the linear properties for optimization. The product of this nonlinear transformation are 16 z variables. You can call them neurons, but they are just the inputs for the next layers. See the equation for the next layer. The outputs Z1s from the first layers, now they are inputs in the second layers. And because they are inputs, we have to estimate more 16 Ws for these inputs. Let's see the code for the second layer. It just apply again the rectified linear function and the output again 16 neurons, but now we call Z2. Now let's add the final third layer. It is a sigmoid transformation that output one variable that ranges from 0 to 1. Let's see the equation for this third layer. This is just the well-known logistic regression in statistics and econometrics. In our data, y is 1 or 0, but the model will generate the predicted values y hat that will be between 0 and 1. That means probabilities. Given that the network is ready, now we have to optimize it. From Keras, we import optimizers. To compile the network, we choose the optimizer root mean square propagation with learning rate 0.001. This is a more robust and updated version of stochastic gradient descent. Learning rate or steps are given by epsilon. Epsilon control how fast the gradient will converge and find the local or global minimum. Epsilon is element-wise multiplied by the gradient to update the W's. This would be the regular stochastic gradient with fixed learning rate. To make this learning rate flexible, we scale by square root of r. R is the cumulative square of the gradient. Then we apply the exponential decay average, controlled by the parameter ρ. The intuition is to put less weight in the very past gradients. In the denominator, we also add a small constant delta to avoid the division by 0. Now let's choose the cross-entropy as a loss function to be minimized, and pick the metric accuracy. Accuracy is the proportion of the correct classify, the p hat c. C0 means correct classify as 0, and C1 means correct classify as 1. The capital Y is the indicator function that counts when the yi, the data, match with the prediction of the model. Then we average these counts to get the proportion of the correct classify. This measure is very intuitive. For example, if you get 0.95, that means 95% of the prediction are correct. In the end, everybody wants to see this metric. But the question is, why not minimize this metric instead of the cross-entropy? Let's see the formula of the cross-entropy. The proportion of the correct classify as 0 and 1, they show up in the formula of entropy. That means that they are similar, but the logarithms, it helps for optimization problem, especially for maximum likelihood estimator. It might be counterintuitive, but the way of maximize the accuracy is to minimize the cross-entropy. As we have a big data set of 25,000 movie reviews, let's separate 10,000 for validation. We do this for both x explanatory variables and the y the labels. Finally, we can feed the model, and we save the results in the variable history. First, we specify the data x and y. Then we choose epoch 20 with batch size of 512. That means that the gradients calculate each time over a random sample of 512 observations. Therefore, the gradients calculate several times, and we cover the whole dataset 20 times. And now we are ready to specify the validation dataset. Now let's see the results. Training on 15,000 samples and validate on 10,000 samples. For the first epoch, the cross-entropy is 0.5 and the accuracy 0.8. For the second epoch, the accuracy is 9%, and for the third epoch, accuracy is 92%. Accuracy increases with epoch, but you might have an overfitting problem. That's why we check the accuracy on the validation dataset. From first epoch to third epoch, the accuracy of the validation dataset is increasing from 86% to 89%. But moving to the fourth epoch, now the accuracy decreased to 88%. This indicates overfitting. It is more convenient to see the results in a graphical format. The history of the model is saved in the file history.history. And let's save it in the history dictionary variable, then you can run other models. Below is the code to plot the graph of the training and validation loss. See that if epochs increases, the training loss decreases, or the cross-entropy decreases, but not for the validation dataset. See that after the third epoch, validation loss is increasing. Now let's see the graphic for the training and validation accuracy. Here's the code. See that if epoch increases, the accuracy increases until almost 100%. That means 100% predict correctly. But for the validation dataset, after the third epoch, the prediction gets worse. Now that you have an idea of the optimal epoch, let's evaluate our model on the test dataset. Here's the code that we ran before. The only difference now is that you pick epoch 4 and we evaluate on the test dataset. See that the maximum accuracy that you get is 93%. That means the model predicts right 93% of times. And this is a very simple model. We have just 3 layers. We are not using regularization, dropout, feature engineering. Potentially, we can easily get accuracy over 95% without any domain expertise in movie reviews. Now let's generate the predictions. We just call the function predict and it passes the 10,000 explanatory variables that you create. For each observation or comment, the model generates a specific probability. For example, 91% should be a positive review, 86% should be a positive review, but this 45 and this 0% is likely to be a negative review. Basically, the model can be deployed to predict if the future reviews will be positive or negative. Thanks for watching my video. Below you can access my other videos that go deeper in many concepts that I use in this lecture.